there's this compelling notion that there's going to be a ChatGPT moment for robotics, where if you get enough
Right.
data, you
Right.
can build a big enough model and you can generalize to all cases. And we're kind of taking the other approach. We're taking the same approach that nature does, which is, you might be able to, instill instincts into a network, but then everything else is kind of learned through intuition in real time, in the moment. And I think humans are very natural with it. Every time you're doing any kind of manipulation task, or even like opening up a stuck door, you kind of very naturally wiggle things and like jerk things around, and kind of feel your way through things in a very um, intuitive nature. And that's really why I feel like this homeostat approach fits well with robotics, because that's what it's doing.
Hello, I'm John Clippinger, the host of First Principles First, and I have the great opportunity to introduce Matt Brown, the founder and CEO of ThoughtForge. Um, and what's particularly interesting about this particular episode is that we're going to be exploring some territory that's generally not covered in the traditional AI literature, even in active inference, but we think is extremely relevant. And it is the resurrection of some concepts from cybernetics, of all places, um, and a particular brand of cybernetics that goes back to the work of Ross Ashby. And I have some bias in this, that's how I was first introduced to cybernetics, and being a TA on teaching his book, An Introduction to Cybernetics and Design for the Brain, many, many, many decades ago. I might add that Ross Ashby, for those of you who do not know who he is, first coined the concept of self-organizing systems. He really was the one to formalize a lot of the ideas behind cybernetics that resulted in certain control theory concepts, such as the good regulator theorem that Carl Friston et al. Refer to a great deal, also a law of requisite variety. But of particular interest here is this notion of his homeostat, and the idea of ultra stability. But before we get into that, I think we'd like to have Matt can talk about his company, where he's applying these ideas to robot arms. And why in the world would you do that? Why? I mean, when you look at, you're up against the Elon Musk of the world, who's raising billions of dollars, and the key impediment, evidently, to his success of Optimus as a home and actually factory robot, humanoid, is problem in dexterity, manual dexterity, just a lot of the problems that you're talking about. Um, so I think this is a fertile ground to introduce ideas that are not normally covered in the general AI, AGI, superintelligence, LLMs. But I think it's extremely powerful, and I think promising approach. So sort of lay down a piece for you. So first, give us a little background on yourself. How did you get yourself in this situation? And then, and then, if we all ask, and then why homeostats? Why ultra stability? Why that? And then how do you apply it? Because I think that's of great interest.
Yeah, and it's a long story, but I think we have time here, because
We
yeah,
got time.
there's a huge amount of breadth of topics that we could cover. I'll start with my background, and because it will get into how I got into homeostats and what we're doing here with robots. So I've been working in AI for about 25 years now. It feels like a long time. I've been obsessed with AI for pretty much my entire life. Just the idea of how does the brain work? Can you mechanize these things? Computers have always been fascinating to me. Growing up in the '80s. So I've been working in AI for a long time, ever since I came out of MIT and UPenn, and from a grad school, working on drones really early on. Then I worked in video games for a long time, on franchises like Halo, BioShock, Splinter Cell.
No, I didn't know that. Wow,
Yeah,
wow.
yeah. So I did a lot of video game programming. Spent about 15 years writing AI for big franchises, and it's such fun work. Really, really fun work. Uh, and then just for, I guess, to show a little bit about my career, about 11 years ago, I left working in games and joined a startup working in deep reinforcement learning called Bonsai, which was really one of the first companies out there. We built the first production grade deep reinforcement learning platform, which was bought by Microsoft in 2018 and became, yeah, it was the Azure Autonomous Systems platform. And then in 2020, I quit Microsoft to start ThoughtForge. But the technology and the approach at ThoughtForge started a long time ago. So in about 2007, and I promise the story's not that long, but in about 2007, deep learning was becoming more and more popular. And I was super excited. I'm obsessed with AI. I'm really excited about this, this up and coming new approach that was starting to see, really big progress, especially in vision processing and things like that. So I did a deep dive on backpropagation and deep learning systems. And if I'm going to be honest, I was really disappointed. It was very kind of disillusioning, I guess, because to me it was clear that this is not how the brain works. The brain is not doing backpropagation. The brain is not just an input output, computational system. And so I was just very disillusioned, and I realized there had to be something better than this. So I started looking in all different places, discovered cybernetics, and just started reading everything in cybernetics. Started with the basics with Norbert Wiener, and there's some really great stuff in there with Stafford Beer and
Yeah.
Gordon Pask. But when I found Ashby's work, I absolutely became obsessed. I felt that there were some really kind of key important ideas that seemed new, even in the 2000s, seemed new, just because nobody had really been talking about them. I went to grad school, I went to MIT, I'm very well educated in the AI world, and the fact that I had never heard about these ideas kind of blew my
Exactly.
mind. Yeah.
Exactly.
And so I started out by just kind of getting obsessed with his work. I started recreating some of his system things that he described in his books, and the homeostat ended up being like my primary obsession. So I started out by just simulating it and implementing it. If I'm going to be honest, I stole a bunch of techniques from in the late '90s. I was working in a field called software radio, which um, it was the
Oh,
spectrum.
yeah, I know that. Yeah, yeah,
Oh
yeah.
yeah, and so yeah, I did a lot of the work that became what's
Oh,
now known
that
as
was a
Houdini
big
radio.
field, yeah.
Yeah, but I mean, at the time, really, what the science was how do you simulate analog systems in digital hardware? And so there's a lot of tricks to how you deal with nonlinearities, which are all over digital systems, which you really need to minimize if you want to accurately, represent an analog system. So I took a lot of these techniques from software radio and used them to implement the homeostat, kind of as an
Oh,
analog system.
interesting. Oh, very interesting.
Yeah, and because you really kind of need to, the conclusion I came to is that you really can't they're not analytically tractable, especially as these networks get larger and larger. The way that the chaotic attractors are defined are almost as random as you can get. It's almost as unpredictable as you can get, and that's kind of how they work. And so I came to this conclusion that you really just need to simulate them, and in order to actually see their dynamics. So I built these analog systems. Eventually, I basically abstracted away all the unimportant parts of the homeostat to
But can
just
I just pause you for a second because it would give our audience a little sense. So when Ashby was doing his work on the homeostat, they were implemented in what 1940s?
he was using recycled bomb parts from World War
Yes,
II.
give a little texture of that. I mean,
Yeah,
so doing what you did, you really had to go back in time,
and
and he
there's
was a
no
very
really.
wonderfully eccentric guy. I mean,
Yeah,
right?
no, he was doing this
And
at a time before digital computers existed. In fact, he had a little bit of an argument with Turing, and they were
right.
arguing about whose system was more generalizable. And I think Turing won the argument in the public eye at the time. But the big challenge for me later on was that there's no really good accounting for how these things were built. They were built with recycled bomb parts. They clearly functioned back in the 1940s, but the way that he did the random number generator was not how you would do it nowadays. I ended up using a lot of his technical journal writing. He has like 7,000 pages of handwritten technical journals, which are, uh, you really have to be in a mood to read through them.
You really
but
I
if you're
was
in that mood,
but the hill you were climbing was and
well, yeah.
by yourself. I mean, you gotta be by yourself. There
And
but
that's why
anyway.
there was a good dozen years between starting that and starting ThoughtForge, and a lot of that was just I was just personally curious, like where this would go. I felt like you probably do that. This was a whole field that was kind of ignored for the last
Totally ignored.
80 years.
Totally ignored. Yeah.
And I'm still learning. If I'm going to be honest, the technology that we're using at ThoughtForge is kind of a very early version of a lot of this stuff. But the amount of potential and the amount of directions you can search in many ways is problematic because I could literally do research for the rest of my life and and not really make a ton of progress other than kind of philosophically. Um, but to me also incredibly intellectually stimulating. It's a completely different way of looking at the learning program problem. And I don't want to get ahead of myself too much, but the way that lately I've been able to kind of express it is, deep learning is doing like function approximation. You give it the giant, data set, and it can kind of approximate an infinite pile of data in some sort of function. And what these are doing are not that. And so I think this backpropagation based approach has kind of been intertwined with how people think about AI these days. And
That's
I
true,
think that's a
definitely.
really tragedy, if I'm going to be honest. And I would argue that what the homeostats are doing are um, the synchronization process. It's doing like generalized homeostasis, but it's really a synchronization process. And to me, the reason I was really interested in this stuff because it really started answering the questions of like what is agency, like what is meaning, and the other thing that was interesting to me is that it put time back into the process. The deep learning systems are kind of um, time invariant in the sense that like the order usually doesn't matter when you're doing inferencing. When you give it an input, it calculates it and generates an output and kind of assumes that the computation is instantaneous. And this is all clearly not biologically plausible in my mind. So the fact that the homeostat is kind of satisfies all these different things that I was curious about really is what kind of kept me going. And there were obviously periods where I was too busy to work on it and things like it was a hobby
Yeah,
project for a long time.
just to pause again, I think that putting time and cost associated is a really important constraint, given the fact that we're looking at the huge computing costs and everything else of the current approach, and so that constraint itself is important. I think in having a viable solution. But anyway, I just want to
Yeah.
highlight that.
I mean, and I want to make sure I don't get ahead of myself because it's very easy for me to skip steps in the explanation and then it's totally incoherent. Because these things are very unintuitive in terms of how they work. And they're very very surprising. Um, but yeah, I also feel like they are. I mean, there are plenty of problems out there where you don't want biological plausible solutions. We can fly airplanes without wings,
Right, right, right.
but I think that not knowing how these natural systems work is also a big problem. But I think, and this was one of the reasons why we ended up in robotics, is that I think robotics is kind of like the killer app in that you kind of need this egocentric agency. You need this kind of fast adaptation in order to do things, in real time. And there's a lot of challenges with, doing things in real time. Like robots, you can't wait a second for a response from your AI model to make a decision about what you're doing. You really need something that's happening in the moment. And I guess the big debate and, what I'm fighting against in the industry is that there's this compelling notion that there's going to be a ChatGPT moment for robotics where if you get enough data, you can build a big enough model and you can generalize to all cases. And we're kind of taking the other approach. We're taking the same approach that nature does, which is, you might be able to, instill instincts into a network, but then everything else is kind of learned through intuition in real time in the moment. If you deal, yeah, and I think humans are very natural with it. Whenever every time you're doing any kind of manipulation task or even like opening up a stuck door, you kind of very naturally wiggle things and like jerk things around and kind of feel your way through things in a very um, intuitive nature. And that's really why I feel like this homeostat approach fits well with robotics because that's what it's doing. It's essentially doing this kind of random search through like a very
Well,
large state space.
could you just pause on that? So there, I mean, you are the curious. There was a well, I think it was a talk that we were at in Montreal. That so sort of there was I think a reference to the curiosity factor. So you're sort of exploring different kinds of variations of something in order to understand it, sort of frame a space. So that that I think that reinforces what the point you're making, is that so you say that comes naturally from this, right?
Yeah, and I think you hit the nail on the head in that this is kind of where this cybernetics approach starts overlapping with active inference because there's like intrinsic value to reducing your uncertainty in the environment, which is like trying new things without knowing what's going to happen ahead of time. Where like when you get stuck, if you can't open that doorknob. It's very natural for you and I to kind of wiggle it in different ways to see what happens. And that's, you're not like thinking through it and logically, but that's what you're doing is you're kind of wiggling it to kind of understand how a doorknob works. And every doorknob is different. So everything's going to have slightly different dynamics. Um, and that's kind of very much like an active inference process
Oh,
in that
yeah.
sense.
Yeah, yeah.
Yeah, yeah. But in terms of how I actually got in touch with Professor Friston is I was mostly I had gotten really far with these homeostats. After working with them for about 10 years. I was working in deep reinforcement learning at the time, and I was able to solve a lot of these kind of toy deep reinforcement learning problems with these homeostats. And that was when I really kind of had this aha moment. Yeah, I was able to, like, cart pole, mountain car, acrobat, a lot of these kind of very simple deep reinforcement learning environments. Being able to solve them with homeostats was kind of mind blowing. And that's also where we saw the efficiency. We were at the time, I want to say we were about 10,000 to 100,000 times more data efficient than deep reinforcement learning systems that we were playing with at the time. And that's where I had a moment of like, this could be really something. But if I went out there and told people that I was going to be using homeostats to do learning systems, nobody would know what the heck I'm talking about and would have very little faith in me. So I would wanted to see what was like the modern field that was kind of exploring these spaces, and that's when I found active inference, and that's when I reached out to Professor Friston, and I made some arguments with him about why I thought these were active inference systems without really knowing that Professor Friston already kind of believed, and he quotes Ashby many times in his free energy principle. And the argument I was making then was that each of these nodes in a homeostat is using this rule ultra stability. And if you look at the process of what it's doing, is it's accumulating this weighted multiply from incoming signals, and then resetting the weights when that accumulated weighted multiply gets above a threshold. But if you look at that from a perspective of these weighted multiplies are like predictions that are trying to get the internal value to be zero, or the furthest from these thresholds, that accumulated weighted multiply could be seen as a accumulated prediction error. So you can look at each of these agents in a network as constantly trying to minimize their prediction error, and that's how I kind of made the translation between what Ashby was doing and what active inference is describing. Now, the mathematics don't line up exactly with how kind of formalized active inference has come about in the last few years. That maybe I don't, but I don't want to get on a tangent. I have a feeling I have a way of that I've been kind of thinking through that.
But is that a limitation of active inference, or is a limitation of what you're doing? You're talking about is if it arguably is it's pretty static, and what you're talking about is something very dynamic, right?
Yeah,
I mean,
and
that
that kind of
yeah,
hits the nail on the head in the sense that I feel like the mathematics, the formal math, the mathematical formalisms in active inference are meant to describe the kind of the body of relationships in it,
exactly.
and are meant to be free of assumptions, and they're meant to be kind of like, this is like the purest way of looking at the relationships. But in nature, when any of these systems are physically realized, there's all sorts of assumptions about the mechanisms and the actual materials that are the substrates that are running the active inference that can completely change the equations. And that doesn't mean that the active inference is wrong, or that the physical manifestation is wrong, but it means that that translation is much harder to make sometimes. And that's where I feel like I am, where I don't feel like active inference's equations are wrong, and I don't think that Ashby's approach is wrong. It's just connecting the dots is going to require more effort because of the assumptions that are being made when you actually put this in a physical substrate. I don't know if that makes sense.
No, it makes total sense, but what you're recognizing is sort of you have some particular kinds of structures or forms of biomolecules that are unique to a particular situation that affect the outcome of the combinatorial abilities, and it is that those semantics, as it were, that become really important local semantics as to being able to achieve the a particular homeostasis, right? I mean
That's
that.
right.
Yeah, and so
Exactly. Those local semantics will change how those equations, those abstract equations, are manifest. And so
exactly.
as a result,
Well, that's
is
going from physics to biology, isn't it? I mean, okay, where
yeah.
semantics,
And
yes,
even like if you look at homeostasis, there's a million different ways of implementing like ultra stability. But because the mechanisms are really simple, I do think it is biologically plausible. I do think there are many different ways that nature has kind of created these mechanisms, and they're also distributed. So like it's not just like there's not a homeostasis cell in the brain or something like that. It's and homeostasis is not even a property of an individual thing. It's a group property,
It's a
and
group
ultra
property.
stability is really the individual property that enables the group homeostasis. And there might be other mechanisms besides ultra
You could
stability.
describe it as if a group property is like a field. I mean, okay.
Yeah,
Yes.
and yeah, and it's and now we're getting into kind of very abstract stuff, but absolutely, especially
Well,
when you
that's
get
all
into
right. I
higher
mean,
dimensions here.
we're
Yeah,
we're not going to do this on the Oprah show. So but I think these are important points to pull out, because I think there is a direction here. But anyway,
and if you look at like Ashby's drawings, and he has some really cool. He hand drew all his drawings in his books and papers, and it's really quite impressive. But yeah, if you look at his drawings of how these things work in systems, they're all drawings of fields. He's drawing arrows. All these things showing
oh
kind
yeah,
of
that's
how the
right. They
dynamics of a system work.
field effects.
Um, and there
But
a lot
you
of them are
don't have
faceless
that. I mean,
portraits.
correct me if I'm wrong, but you really don't have that perspective so much in active inference as now it is.
I don't think so, and I don't want
Okay,
to pretend to be
that's
too
what
much
I'm
of an
getting
expert
at.
of
Yeah.
expert. Yeah, but I get that feeling. And I feel like now, because they have the mathematical formalisms, so much focus is on taking those mathematical formalisms and then implementing them in different ways and doing experiments. And not to discount that work, that's super valuable, but that's very, very different than looking at the set of relationships, in kind of an abstract way, and seeing how this can apply in different places. But that's one of the reasons why I like active inferences, because it is so abstract and can apply at different
No, it's
times,
true.
at different kinds of scales. Yeah, yeah.
It's true. So you decided to go after robot arms, and why is that problem interesting? I mean, what's the big
It's
deal about picking up and putting it into something? Why?
Yeah. I mean, well, yeah. As you can see, it's much more challenging than people think. And robots are there's just so many things that make robots difficult. Um, there's the real world is incredibly dynamic and unpredictable. And even just the physics of like of a hand is super unpredictable, and anything can happen. And then with robots, you also have time constraints. Even in video games, you have real time constraints in terms of how quickly to make decisions. But the time it takes to actually make a decision about moving a joint in a robot impacts the quality of that movement and that behavior. There's I don't actually think that they're going to get the data sets that they need to build the ginormous models that they want to perform household chores, for example. And even if they do, there's also going to be challenges of getting that to run on a piece of hardware that can sit in a robot. And then and if you do, there's also going to be power constraints. I don't want to. I've eaten my words many times in terms of AI predictions over the years, so I don't want to make any
Sorry.
predictions about. And it's anybody's guess as to whether or not they're going to get there. But I do believe that there are better ways to do it. And I also am not completely a zealot. I think we can mix and match. I think I've even considered mixing deep reinforcement learning with these kind of homeostats, in the sense that maybe you use deep reinforcement learning to come up with high level abstractions of when to water the plants versus vacuuming the floor, and then you use homeostats to do the actual physical manipulation of the world, and that would kind of be win-win. Right now we're having a challenge with these homeostats in terms of how do we move upwards in complexity in terms of long-term horizon planning, and then with deep reinforcement learning, if you can reduce the action space, by not, instead of having to actually come up with 20 degree of freedom joint controls for fingers, instead you're coming up with grab that cup and move it into the cabinet. It drastically shrinks the amount of data that you need to train a deep reinforcement learning model to do something useful in the world. But I think the real challenge of what's missing, I think they can already handle the high level stuff. I think what's missing in the world right now is that low level dynamics. And that's why we see all this money towards visual language models, towards diffusion models. And I think visual language models are not going to get there in the end without tactile data and force data. I think
That's what I was thinking about, the whole tactile data. I mean, so Rodney Brooks did a paper on that recently, right? And
Yeah, I think, yeah, that's right. And the reason why this is going to be a real problem is getting the data. With ChatGPT, they had an internet scale data set to train, a model on how words are put together. But that doesn't exist for that doesn't exist for robot data, first of all, but it's
To get
especially hard to get for force data.
to in order to get that, you would have to have some kind of representation of a tactile. I mean,
Yeah,
in order to say,
and
you'd have
these
to
are
build a
famously hard
device
to.
that actually created the data, right? Which you don't quite know, right? I mean,
Yeah,
right.
and you can try putting that in a simulator, kind of like a video game. You can put like force sensors in there,
That's
but
true.
they are not nearly accurate enough. The difference
Wow.
between a simulated force sensor and like a real one can be an order of magnitude or two, and like it's almost useless from a reinforcement learning point of view. I think right now we're also seeing a wave um, of data collection techniques around teleoperation, where you teleoperate the robot, and they'll put tactile sensors on the fingertips and things like that to get that data. But it's I think a lot of people don't understand how much data you really need to get
But
these
this is
things
the
useful.
point. So Meta has this test that they're using to for robots in the home, but you're familiar with that. But it's virtual. It's all a simulation, right? I mean, and so even if you perform well on that, I mean, so Versus it talked about performing, but it was like in a virtual world, which it is not even close to the real world. So yeah, okay.
Yeah, no, and I face this with video games. It's way easier to make a video game character that can interact in a simulated world, and a lot of the challenges there are at the high level. They're deciding, okay, I need to go open the cabinet, I need to walk in front of the cabinet, grab the handles, coming up with those things. What they're not really going to be able to solve in simulation is, how do I grab the cabinet in a way that doesn't rip it off the wall or like, doesn't twist it, because let's say if you have all the cabinets are perfectly the same, maybe you can do it. But some cabinets open a little bit differently. They need more force or less force, or maybe they were installed incorrectly, so they're at an angle. And so if you try to open it, you have to kind of
So
you have to
that's
kind of
where
treat every cabinet
the
as
homeostat would be able to experiment with different options around how to. Okay, this is not working. Maybe I'll go over here. I'll go explore different options, and then not too much pressure. So
yeah,
I
and it may not be obvious, but how you take a homeostat and make it do something useful, and that can be kind of complicated. But essentially, what we're doing is that we're representing the goals of a task as like homeostatic set points. So like if you want to open a cabinet, I basically have some sort of as kind of a sensory input into the model, I have the distance from the cabinet handle to
I
where I
see.
want it, for
I
example.
see.
And
I
then it
see.
would learn to figure out how to grab the handle and move it to the
Well,
target
that's
position.
interesting. That's
Yeah.
really is
Be-
that novel? Is that
yeah, I don't think not I mean there have been very few people who have implemented homeostats. I don't think Ashby ever connected his
I don't
homeostats
think
to
I've
external
never
thing.
heard anyone say what you just said.
Yeah, and so I mean, if when basically a lot of the work I did was abstracting out, like making abstract homeostats that you can build into arbitrary networks, and they're all trying to predict their neighbors is one way to think about what they're doing. So if you connect kind of environmental signals as incoming, and it doesn't know that it's not a homeostat, it's going to try to figure out how to make that. Okay, let me figure out how to explain this. Let's say you have a sensory signal going into the homeostatic network. The network's going to try to figure out an equilibrium that causes that node to be zero or below its threshold, even though this is not a homeostat that's generating the signal, it's a sensory signal. So then if you so it's going to try to figure out how to predict that external sensory signal there by generating kind of predictive signals from deeper in the network that counteract the signals that are coming from the environment. And then likewise for motor
Whoa.
actions, we do the same thing. We basically we say, okay, these nodes here are going to be connected to the external environment. And if the signal value is above zero, then it's going to move the motor in this direction. If it's below zero, it's going to move the motor in the other direction. That kind of thing. And then what will happen is that the synchronization. So it first the network will synchronize with itself. The neighbors will synchronize with each other. And then if it can synchronize faster than the environment is changing, that homeostasis will extend out through the motors and in through the sensors, and you can actually get it to modify the motors in a way that makes the sensors easier to predict and go closer to zero. I don't know if that makes sense,
Well,
but
that
that's how
makes
we're basically doing motor control.
that's very cool. And,
Yeah.
well, so I'm gonna replay this. This is to my understanding of what you just said, because when we started talking about that, I mean, I was thinking about a Markov blanket too. Okay, so it is being able to distinguish between yourself and the environment and maintain the requisite variety that then allows you to then act upon the environment in order to achieve your goal as a form of homeostasis. Is that it?
Yeah.
Yeah,
And you can kind of think of it as like generating this synchronization manifold. You can kind of imagine like, um,
yes.
I mean, it's almost like a collective intelligence kind of thing where each
It
homeostat
is, yeah.
node is like trying to maintain its own validity. And then it will form collectives internally, like subnetworks within the network that end up representing concepts. But the idea here is, it's some concepts are more complex than others, so you need larger subnetworks to kind of form them. But these concepts, without connection to an environment, are abstract and they're just randomly generated. But when you connect them to an environment, the environment ends up conditioning the network, and
That's
vice
right.
versa. And there's this kind of
Vice
back and
versa,
forth. Uh,
it's bilateral. That's really that's really interesting. I mean, so play it back again. So Michael Levin talks about light cones. Are you familiar with his work on light cones?
um,
Uh,
Not in light cones. I read his work. I think Mike
Well, I
Levin's
mean,
fantastic.
what you're saying is, I think you solved, at least, and this is my preliminary understanding, is that uh, you actually, in your way of framing it, solve the problem of an individual of light cones synchronizing themselves as a whole into an outcome. And that's what you just described. Now that's really
Yeah, I mean,
you
and
should write
there's
about this.
well, and that's the thing. I don't feel like I don't. I'm not much of an act. I don't write papers, and because I don't feel like these are my ideas. I feel like these things pop up in perceptual control theory and
I know,
active
but no one
inference.
pulls them together. I mean, but the value is in pulling together in the way that you're talking about, really,
Yeah, it's definitely something
and
very few people are
seamless
doing.
connections. No, no, that's no. I think you're being too modest. And anyway, uh,
It's definitely hard to
yeah,
explain to people what we're doing. We just brought in some new engineers on our team, and it's I love it. I love the educational process because you can see their minds kind of explode a little bit when we were describing what's going on. And now that we've been working on it for many years at this point, showing robots actually being controlled by homeostats is like it's pretty mind blowing, especially if you try developing your own homeostats and homeostatic networks. Like they're if you get it just right, it's kind of magical when they synchronize and they reach convergence and they reach equilibrium. And then imagining how that can control a robot is kind of mind blowing in terms of seeing it come full circle because it's super abstract what's going on. And the network is generating like perceptual expectations and motor actions in parallel. And it's not like a deep learning network where you take an input, you compute it, and you generate an output.
no, no, but
It's
it is
always
more like
simultaneous.
is
Yeah.
more like you're describing again more like a Markov blanket where you have actions and observations and policies being all happening simultaneously,
All
right?
simultaneously. Yeah. And in order for that to really work, you have to kind of incorporate time as a first class concept, And so when I talk about these networks and like sensor information coming in, there's actually like a clock. In a robot, this is actually like physical time. Every time the time advances, signals are propagating through the network. And it's super recurrent. So like, there's all these forward and backwards connections all through the network. So once gets inside the network, it's just a big mix where signals are just flowing in all directions. And then somehow out of this kind of chaos, we get motor signals and sensory signals coming out in parallel, meeting the environment. And the idea here is, and it somehow is able to do useful things is pretty crazy. Definitely takes several paradigm shifts for people, especially people, if we bring on a new engineer and they're used to dealing with, traditional deep learning systems, takes several paradigm shifts to get their head around what we're actually doing. It's very different. And I'm excited about this. I don't see many people out there doing
Yeah, but you're
really
solving a
new
problem a
things.
lot of people are having a hard time solving right now. I think this is a core problem, right? I mean, if this is the heart of a problem of any kind of synchronization of multiple agents within and towards a joint outcome consensus, where they may call it knowledge sharing or belief sharing or something like that, but it's arriving at a coherent a coherent set of beliefs for all of them to synchronize around, right? And this is what you're describing that can happen, and putting the time factor in, and it can happen in sort of some kind of real time setting. If what you're talking about, which is what people do when they move and act in the world. And that's really it's big stuff.
Yeah, and
Uh,
I can see like this is why I kind of think of what I'm doing as more of engineering is because um it's very difficult to analyze these things. Like, we've built a lot of our own internal tools, and there's a lot of stuff we can do, but they're incredibly chaotic, complex systems, and time is always moving. So so as time's moving, the networks are kind of redefining how it's constructed, how it represents the world, what what are even the abstractions that it's using to represent the
well, then,
world.
so there is a question, say that if you're wanting to have trustable AI, you should be able to explain
I
why
mean, yeah.
it did what it did, right? Now, is there any form of this variant of this that can explain it, or is this like auto
Yes, but
magical?
it's very similar to like humans explaining their actions, where it's like you can kind of justify it, but do you really know why somebody made a decision? Even if you ask them, you can't really be sure if they're
That's a really good point, because
but
the justification. I mean, the neuroscience shows at the end, you say, well, the rationale always follows the emotion, right? And it's retrofitting. You say, well, to justify it, but the emotion is what really created the. And
but
from that,
on the plus
you
side, though, we do have like the ability to actually look at the network and the network state, unlike you can with other people's brains. So we do have things where we can, like, for example, we call them energy levels, but you can kind of look at the state of subsections within the network. And if, for example, the average energy state of the subnetwork that's near a particular sensor is really high when an action is taken, you can say it was that system that was driving this decision.
oh, that's really important.
And now
Okay.
it's not very specific, but you can get some ideas that way. That's what we've
So
been
you
kind of
have a
trying.
sense of what part component subsystem contributed to the overall, was playing a role in it.
That's
That's
exactly right. Which homeostats were the most disturbed during the period that this
this
decision
is
was made,
really, really
and you
interesting.
can kind of like say, oh, you can look at the region of nodes around each particular sensor, and you can say, or environmental signal, another way to put it in an abstract way. And you can say, oh, these were the factors that were the primary drivers of this decision. And once, if you want to get more detailed than that, then we get really into like definitions of causality that are really kind of difficult to make, right? Because it's distributed. The way that these networks actually work is inherently distributed. There's not like one node in the network that's like, I make the decision and then everything else flows. So these decisions are kind of distributed, and so there's you can make inferences, but you can't be absolutely sure of anything. Any conclusions, I guess, is one way to put it.
No, wait. Let's focus on it. So you're saying, so it's fully distributed. So you cannot, there's no causal chain that you can identify in that, or is that
It's almost intractable because of the way, as soon as you hit the network, as soon as the sensory signals hit the network, they go in all directions and then come backwards and forwards and intermix with the past. Um, Now you
that's really
can make general correlations. You can say, oh, this sensory signal was highly disturbing to the network when it took this action. And so you can make a good assumption that it was probably whatever it did that was unusual was probably due to this unusual signal that came in. It's just hard to make that a 100% guaranteed conclusion, because it could have been something that happened
oh,
several minutes
well,
before that was bouncing around the network, and then something unusual happened. It caused it, a cascading effect that I don't know. There's always edge cases that it's hard to account for.
but you okay, but you could make the claim that it will converge. Oh, that is that.
Yeah, and well, the networks will converge absolutely. It In isolation, the networks will always converge. When you're
Oh,
connected to
good
it
point. Yeah,
Yeah,
good
when you're
point.
connected
Good
to an
point.
environment, it
Good
depends on
point.
the
When you're
environment.
talking to environment, no, no. But then if it's if you're linked to an environment of a certain property, then you may have a likelihood of whether we converge or not converge, right?
That's right. And honestly, this gets back to Ashby's law of requisite variety. As
That's
long as the
exactly where I was
network,
going. That's
yeah, if the network can generate, an expressive enough motor and sensory expectations faster than the environment's changing, it will, and that's kind of the key. We basically want to make sure that the network is always converging faster than the environment can destabilize it. But if you imagine you're trying to like predict lottery numbers, as an example of an environment that's too complex. Like the network that you would need to be able to predict the next lottery numbers that come out like tomorrow. It's like an impossible problem. And so I wouldn't say like you might be able to converge the network. But it's every time a new lottery number is picked, it's going to get destabilized because it's going to try to learn something from it. Um,
What
um,
is this a good time to bring up your diagram, or do you think
yeah, yeah. And And this is basically just taking a look at a kind of our internal homeostat debugger. And what you're going to see is, so we have these networks of homeostats. These are what you're actually going to see is a fully connected network. And you're actually seeing the accumulated prediction error, that state value that's inside the homeostat, going to equilibrium. If you want, I can get that up and running here real quickly. And there's something kind of interesting here that the reason why I like to show this is because of in my mind, what ends up getting learned is almost like a pattern, and it's different every time. But I'll let me share my screen here really quickly, and then I'll kind of talk through it a little bit here.
I mean, so each of those nodes can be considered as agent, is it correct?
That's right, and just kind of like actions of agents, are kind of groups of people, and you can kind of look at their behavior as individuals or as groups. And this is just pause at the moment. So I'm going to go ahead and like unpause it here just so you can kind of see what's going on. And one thing that I've toggled on in this debugger here is this auto scaling, which means that so actually, let me pause this and describe this a little bit. The network here has already spiked. So this is a network in isolation, not connected to environment, and it's already reached equilibrium. But as time goes forward, because I've set the auto scale, as the values go to zero, it'll zoom in closer and closer and closer into the signal to see how it actually reached convergence. And what I find is really interesting is usually there's a pattern, and the pattern's different every time. But what you're actually looking at in that pattern is what is the set of internal relationships that it has decided on to reach this equilibrium. So you can see, all these spikes here have already kind of reached equilibrium. But as I unpause this here, you'll see the scale zoom in, and this will keep zooming in until you get to the floating point error of the chip essentially here. But you'll see that the values kind of have this pattern, this relative pattern amongst themselves as they're dropping. And you can see, I'll pause it here real quickly. We're already down to the 10 to the negative 28 scale as it's kind of dropping to zero. But you can see that they're not just all just going straight to zero. There's this interplay between this node here, generates this signal. This node here takes in that signal and generates this signal. And there's a little dance that gets played as it kind of
Is that to
converges
say
down
that
to zero here.
they're trying to synchronize among all the nodes in order to get to know their neighbor, therefore to get to know a coherent collective a coherent collective homeostasis? Is that
Exactly. And so this is at the point where it's basically come up with that set of relationships, and you're just seeing it play out as it goes down to zero. But those relationships, so this is basically what it's learned, and it's arbitrary. When you have like an isolated network like this, it's going to be different every time because it's going to be whatever is the first set of self-consistent correlations. And you can imagine this as like a nest of overlapping positive and negative feedback loops. And this is the point basically where they've reached perfect balance, and they're kind of driving towards zero here. And this will just go for a little minute here, and then it'll go to zero because the floating point error on this computer can't go any farther, essentially. And it's just kind of a fun visualization to show you know uh, what that process looks like under the hood in terms of what's going on.
so? I mean, so I'm interested in it from a variety of points of view. I mean, one of the things that we're looking at is in markets and how I mean, how consensus is achieved. Typically in markets, you have an arbitrage between different parties. But what this is a synchronization across all agents to achieve a sort of a field right, a
That's right.
field coherence. So it's not one party versus another. It's not a bid and ask system. It is actually a homeostasis or an outcome that reflects all of the sort of resolution of all the permutations of different parties that is possible to do
Yeah, and in an
you know,
abstract way, you can imagine them all either competing and cooperating and like jockeying for relevance in the network. And each network starts out randomly, and that's why you get different outcomes every time. Everybody kind of starts on the same plane. It's a fully connected network, so it's symmetrical across all 20 dimensions, for example. But when you actually have a real network in the real environment. Some nodes are going to be more important than others, and are
yeah,
going to
yeah,
have
no, no,
more
no, no,
stability
no,
and that
no,
that
no,
kind of
no.
thing.
That's
Yeah.
really interesting.
Yeah, no, it's without context. That video is just kind of arbitrary and random. Looking at a bunch of like one-dimensional oscilloscopes. But to me, it's very hard to visualize what's going on in these networks. And so I like to show that because it kind of shows what it looks like when these systems actually reach equilibrium and reach a convergence. And so you can imagine, how that spike goes to zero. We're basically doing that constantly. So as a robot's performing a task, initially we start these networks that are random. Like you're going to have a lot of spikes at the beginning while it's kind of reaching, a more stable region of high dimensional phase space. But the idea here is once you've actually reached that, the environment doesn't change as much as you might think it does. And so, you'll have transient destabilizations occasionally. But for the most part, it's really easy to maintain that synchronization manifold. Like in terms of like stability, we even had to come up with, does it mean if the network is stable, does that mean nothing is destabilizing? None of the nodes are resetting? Well, that's never really possible. These things are always kind of transiently adjusting and tuning based on the environment's fluctuations, for example. So you kind of have to set thresholds. If the network, for the most part, if 99.9% of the network isn't changing, we consider that to be stable, for example.
That is really cool.
Yeah.
I mean, that is a very different mindset. I mean, I think it takes a while to digest that the ramifications of that, but that is extraordinary.
But yeah, no, it's super fun to think about. And to that degree, what does it mean to be when the network is updating? Is it the same network? 5 minutes ago as it is now? There's all sorts of philosophical questions that I don't really have answers to, but like are fun to think about in terms of my own network.
Well, now, what about? I mean, so how does it result in performance of your arms, and you can do things that say others can't? I mean, how does that translate itself into latency issues of latency that you were talking about earlier?
Yeah, I mean, we're still relatively new in terms of like technology and capabilities and things like that. But it's really interesting the kinds of things that you get. We can deal directly because we don't require a huge data set ahead of time to build a model that's useful.
So you don't have the training costs
That's
that
right. And I'm not dependent on a super accurate simulation. There's what's called the sim to real gap, where if you train a model in simulation and you put it out in the real world, deep reinforcement learning models are super brittle. So any kind of differences between the simulation and the real world will cause the model to be completely unpredictable. But for us, it's as long as the simulation is somewhat roughly representative of the task, once we put the model out in the real world, it will, within a couple of seconds, adapt to whatever differences there are.
wow, wow, wow. So I see. So you can contextualize it in a particular domain or niche, and then it learns to adjust and adapt within those domain parameters. That's really
That's right. I mean, some of the examples of stuff that we're doing right now are things like soft body insertion, so like wiggling little rubber parts into like a metal housing, useful in manufacturing. But you can't. It's really hard to do with vision because you can't really get a camera in there, and it's very natural for humans. Like we can very easily feel with our fingertips, if we're applying too much pressure or not. And if you try to do this with traditional robotics, you're very likely to break parts, or it's very very challenging to do. But with this, you can kind of give it very kind of broad, still low level goals, but higher level than like specifying certain forces and things like that. You can say, for example, make sure that the forces that we're feeling during insertion are perpendicular to the direction or in the opposite direction that you're inserting. So that way it will naturally adjust its arm to be aligned with the insertion just based on the force feedback sensors you're getting. So you can kind of set these kind of high level goals and constraints, and it will kind of figure out how to modify its behavior in real time without having a whole data set ahead of time.
That's cool. That's
Yeah,
very cool.
the fact that we don't need much data is a huge win. A lot of people are very sensitive about their data. And manufacturers and things like that, they don't want to necessarily give an AI company all the CAD models for their materials. A lot of them don't have CAD models for the materials, and even things that we've seen is there's a lot of variability in manufacturing. Like even if you know what a part is supposed to look like, sometimes these vary. And if they vary by a few millimeters, that can cause insertions to fail. So having something that can treat every insertion kind of as a unique thing, the same way that we do, has a lot of advantages. And having it adjust in the moment to whatever it's encountering is important. Yeah.
Very cool. Very cool.
And we're a long way away from like AGI, and now we're getting into like more philosophical. I don't actually think we need more human level sentiences on Earth. I think there's plenty. I kind of envision this being more like used for ants. I'd rather create ants, things that are very loyal and intelligent enough to be useful.
Well,
But
you and Dennis, Daniel are into the ant world.
that's right. That's right.
Well, I do believe we can get different levels of sentience. I mean,
I mean, I think we could eventually. It's not that I don't think we'll get there. It's just I don't know if we want to get there. I haven't figured that out yet. If we want to create another class of thinking sentient beings that to compete with, let me put it that way.
well, I believe it's all symbiotic. So I'm a positive. I think that
well, yeah, no, I agree. I think we're much more likely to become cyborgs than like create a new class of creature. I think we're much more likely to create tools for ourselves, and self-enhance. Um, And I think that is very positive. I think we're already cyborgs in my mind.
oh yeah,
How many people
certainly.
can
No,
live without a cell
definitely.
phone? Yeah.
Well, is there anything else you want to cover in our talk here that we haven't, or what the points you want to make?
Oh man, I mean, I didn't come in here with an agenda. This is just super fun for me to talk about. I don't get the opportunity to talk about Ashby and homeostats for the most part, just because there are very few people who even know what they are or have heard of them, let alone are interested in how they can be useful. But I definitely think that there's huge potential in this direction, in terms of and there's tons of topics we could talk about here. If maybe this is for another podcast here, in terms of what characteristics does an AI system need to have in order to be something that's uh, better than deep learning. For me, there's some easy criteria to look at in terms of like operating at critical states, and things like that, so that you can have fast learning. Like I feel like right now
Yes.
backpropagation requires an enormous amount of data just because of the way that these networks operate. And to me, getting towards the complex systems and getting towards you know getting away from the input output kind of paradigm is going to be super important to understand even what intelligence is. I feel like the entire AI industry has gone forward in a direction without really asking the question of what intelligence is. What does it mean to
Well,
be
I
intelligent?
totally agree. It's assumed they know it is not something that's easily known, and there are many different opinions on it, and it's like a given. And no, what is super intelligence?
Yeah.
What AGI? I mean, come on.
And the thing is, like, that's separate from, like, it's clear that these systems are useful. I don't want to say that LLMs are not useful and like deep learning
Yeah,
is not
no, no,
useful,
no.
but it's not intelligent in my book. There's a big difference.
Well, I think they mimic certain parts of human capability. I mean, they're able to mimic and capture certain kinds of structures. I mean, and I'm compelled by the doing things that I couldn't do that
Oh
I'd
yeah.
like to do, and
And I guess
and
I should be
and
more
and,
specific.
and
They don't have agency, is what I would say.
no, and no, but this is the whole thing. It says, and I'm really intrigued about applying an agency framework to the homeostat in the way that you started to do, and the fact that you took the time to read all of Ashby's handwritings and dive and abstract that out is like, well, that's a major task, but I think a very valuable one, and to inject this notion of a homeostat into I think the general way of understanding alignment, symbiosis, intelligence, agency, I think this is sort of fundamental to that.
I
Um,
agree. And this is why I've done it. I'm just obsessed with this idea and these ideas. Um, and at some point here, I might pick your brain about advice. You can see the challenge in me writing a paper. Reality is I would need to write 100 papers. I think kind of going back to the early roots. But this is where the challenge I have in the active inference community is because I haven't really been able to write a paper that explains a lot of this in kind of a concise way. It's hard to fit into that environment. And maybe active inference is the wrong place to be publishing.
but I think that it's broad. I mean, I think the trick in a paper is to find a use case or something that you can illustrate all the different parameters of the approach. I mean, so if you have a network, I mean, I mean, I'd love to, I'd love to discuss that with you at some point because I think it's important to pull these ideas out because I think they have broad applicability. And I do think that in order to explain it, you've got to map it into certain ways in which people currently understand. But I think framing it through a agentic framework of synchronization, uh, I mean, it's like what's a problem space that you could approach that could really illustrate the richness of it, I guess, is one of the ways of thinking about it.
Like that. And I need to think about. I don't have a good answer off the top of my head, but I like that. And I think the synchronization and talking about the agentic nature of it, I think is kind of getting at the really interesting core parts of this. I think. I spend a lot of my time on the mechanisms and the engineering of these things. But at the end of the day, that's philosophically what's really interesting here is, and I don't even want to say that these things are, what is it? How do I prove that something has agency? I mean, I don't, I'm not even sure if I can, how I
Well,
go
that's
about that.
Mike. Michael Levin talks a lot about that. He will talk about very simple processes that he says are agentic. He sees that as being fundamental.
Yeah.
And he says
Honestly, I need to look at more of
it's
his
a
more recent
prism
work.
by which you look at things. If you don't look at it, you're not going to see it. But if you see it that way, then so it is kind of a framework. And I think that's part of the when you look at Ashby and when I study cybernetic, you have agency of the cybernetic but it's not this notion of embedded agency that is really intriguing, and the convergence around a shared coherence, homeostasis. But anyway, this is great stuff.
Thank you. And
I
I, that's,
laud you for your ability to pursue it by yourself. I mean, I know it's a it takes a lot of
I'm slowly growing a crowd. I feel like I've been kind of ignoring the people who don't understand it because I get it. It's super hard to follow. But even within my employees, it takes people a time to to understand what we're doing. But we have a growing Ashby fan club
No,
at my
good.
company.
But I have to say, when you take Ashby and combine it with Friston, then you're getting double complexities
Oh
here.
yeah, this is probably, and I tell people. I mean, I tell my employees this is probably the most complicated set of ideas around right now that people are even thinking about. Yeah, it's and also there's for how old Ashby's ideas are, there's a huge amount of fertile ground for exploration. Like there's literally there's an unending number of experiments to do. Let me put it that way. And
I
it's kind of
agree.
shocking to me that how few people have gone that direction. Um, but and
But,
I guess I'm
I
too young
mean,
to be a
this is another
cyberneticist. But
topic, but I find that and having sat on a number of PhD committees and teaching at MIT and Harvard and stuff, they don't they don't teach first principles to a lot of their students and say, here's a hard problem and here the way and build on it. It's sort of that, well, who's the speaker for the week that's going to talk about their project? I mean, so you don't have this grounding in sort of what are the really deep, hard problems and how they're being solved, particularly in this field of intelligence, because we talk about, intelligence as a given and no. I mean, I remember Ashby, I mean, my advisor is saying, well, there's no having memory may be good and may be bad. It's not like there's everything is optimal, right? It's like, oh, okay, like it depends on the situation that you have as what is intelligent or adaptive. Yeah, and well, that's a big so the fact that you can get perfect scores on in your SATs is, I mean, doesn't mean it's adaptive in another setting at all. That isn't the universal super intelligence, right?
And there's
That's
honestly, I find a lot of parallels between this and like evolutionary theory, but just
yeah,
like
no, oh, very definitely, very
yeah,
definitely.
yeah.
Well, all right. I think we're ready to roll it up. I really enjoyed this, and good luck. And
This was
I
fun.
encourage you to get these pieces out there in some published form.
Yeah, and if you want to do this again, let me know, and we can get deeper on
Yeah,
any
yeah.
topics.
Well,
But
yeah. Let's bang our heads on this. This is good.
this is a lot of fun. This is a lot of fun.